In biochemistry, we deal a lot with weak acids and their conjugate bases. This varies from thinking about making buffers in the lab to stabilize pH and thinking about amino acids and the various side chains that can be protonated or deprotonated, and when they're going to be protonated or deprotonated, and what effects that's going to have on the protein function and the protein's overall charge. So, in order to talk about all these things, which are surrounding pH, we need to talk about pH as well as terms that sound like pH but are actually different than pH and are different from one another, but they all sound similar. So, let's go into those definitions and then we'll go into what they all mean and how to interpret and use them.
The pH is a measure of free proton availability. It's a measure of the solution, and it's going to be the combined effects of all the acids and bases in the mixture. The pKa, that's the measure of an individual acid site strength. So an individual deprotonation site will have a pKa. And the higher that value is, the weaker the acid, the lower it is, the stronger the acid. It represents the pH at which half of it is protonated and half of it is deprotonated. pKr, that's just a term we give for the pKa of an amino acid's R group or side chain. Some amino acids have them, some don't, but that's what that's for. You also see that there's this point called the pi. The pi is the isoelectric point. It's the point at which a molecule is electrically neutral, so it's uncharged. And so if you have a multiprotic thing, you have lots of sites that can act as proton donors, you're going to have some point at which that molecule is electrically net neutral, and this is your pi. This is your isoelectric point. We can calculate that for like anything that's multiprotic. So it could be like an amino acid. It could be a buffer molecule that has multiple protonation sites, or it could be an entire protein. Thank goodness for computers. All of these different terms, they're all connected to that pH though, because that pH is a measure of the free proton availability, and so that's going to influence whether or not that you see something in its protonated or its deprotonated state. So let's dive in. The Cookie Monster's coming to town. Let's go to the party.
Just a quick terminology note is we often use this abbreviation HA to stand in for a weak acid, a conjugate acid, and we use this A minus to represent a conjugate base. But note that a conjugate base is not always negative and a conjugate acid is not always neutral. That's just kind of this generic nomenclature that we use, and so you'll want to get used to seeing that. If you think of the pH instead of in terms of just like protons, if you think of it kind of proton jar, we'll think of it as a cookie jar. If you have a full cookie jar, this is like you have a high proton concentration, you have a low pH, you have an acidic environment. But if your jar is pretty empty, this is like having a basic environment, a high pH. Now, how full that protein jar is, that's going to be basically your pH. But remember, it's an inverse log. So the fuller your cookie jar, the lower the pH, the more acidic the environment. So you have this cookie jar, say your water. Based on the autoionization of water, you have some amount, a very, very small amount, but still an appreciable amount of ionized form. So of your hydronium ion and of your hydroxyl ion. And so the hydronium ions, what we're going to be caring about here, that's our cookie jar, that's our proton, because remember, those protons aren't just floating around as H+, they're latching onto a water molecule. So your water, you start out with some fullness of your cookie jar. But now what's going to happen? Now you invite over some friends. You invite over some friends for your party. And some of those friends, they're going to come and they're going to come with cookies. And they're going to come and they're going to donate cookies. And those friends are going to be acids. But some of the friends, they might be more generous with their cookie giving than other friends. So some of the acids are going to donate to that jar, even if that jar is already really full, because they're just so generous. They're just going to donate it no matter what. And so that would be like a strong acid. But what if you have something that's kind of more wishy-washy, like, well, I guess I'll donate, but I kind of want the cookie for myself as well. And so therefore, if the cookie jar is already pretty full, it might think like, okay, well, there's plenty for other people, so why should I donate my cookie? I'll hold on to my cookie.
And so this would be more like a weak acid. And only when a protein jar was getting really low, only when there weren't enough cookies for everyone to go around, it might go ahead and give it up. And so really it's not this simple. Really what's happening is that if you have stronger acid, it's going to be less likely to hold on to that proton. It's less likely to hold on to that cookie. But at a higher proton availability, when your jar is fuller, when your pH is lower, there's going to be lots of cookies around so that if it drops its cookie, you can find another cookie. But if that jar is pretty empty, then if it drops its cookie, it can't really find another cookie very easily. And therefore, the proton availability, the pH, is going to directly influence whether or not you're going to find that acid with a cookie or without a cookie, whether you'll find it in its conjugate acid form with the cookie or in its conjugate base form without the cookie. Speaking of bases, what if you add a base? What if some of your friends, they come without a cookie? Some of them come really, really hungry, and that would be like a strong base. They're going to take a cookie even if that jar is really low. They really want that cookie. But then there's going to be friends that maybe they're like, I'm hungry, but I mean, there's not that many cookies. I don't want to take them if other people need them. And so that would be more like a weak base. And again, it's not really like this. It's not like that. It's just that they're not going to hold on to them that tightly. And if they're not holding on to them that tightly and there's less of them around, well, they're more likely to not have a cookie if you were to go and find them at the party. But if there's more around, then you might be more likely to find them with the cookie. So at the end of the night, how many cookies there are in the jar was going to depend on how many of each type of friend there were and how greedy or generous they were. And so how do we describe greediness or generosity? Well, typically we actually describe it in terms of the generosity because we're talking about the acid. When we have a value called the pKa, so that pKa, that's going to be the dissociation constant of the acid. So it's telling you about how much of the acid is going to deprotonate when you get to equilibrium. And so at this point where you have the pKa, this is going to also be the pH at which half of it is deprotonated and is thus in its conjugate base form. So half of that acid has given up its cookie and it's in the conjugate base form at that pH. Because remember, the pH is going to be a measure of the proton availability. It's going to be a measure of how full that cookie jar is. And how full that cookie jar is matters because different friends will give and take depending on how much protons are available. So some of them, remember, they're not going to give it up until there's not very many in the jar. And so that would be like your weaker acid, where some of them, they're going to donate that cookie even when the jar is really full. And that would be your stronger acid. If we're talking about that jar being really full, what we're saying is that there's a lower pH. And if we're talking about the jar being really empty, we're saying there's a higher pH. And remember that the pKa is going to be the point at which half of it is protonated or half of it is deprotonated. If you have a pKa that's lower, what this means is that half of it is going to be deprotonated at a lower pH at a fuller cookie jar. So basically, this is your stronger acid. So a stronger acid is going to have a lower pKa. Conversely, if you have a higher pKa, what this is saying is that you have to get to that cookie jar to be more empty, to be more basic, more alkaline, higher pH, in order for half of it to be deprotonated. And therefore, we can compare the strength of different acids by comparing their pKa's. And the lower pKa, stronger acid, and a higher pKa, a weaker acid. And so when we're dealing with weak acids and bases, we can still talk about them being like stronger or weaker, but we're still within this weak acid base category where we're not thinking about it being fully dissociated, but instead you're going to get some amount of the conjugate acid and the conjugate base. And what proportion you're going to get is going to depend on your pKa, as well as the pH. So it's going to depend on what's around it. How strong an acid is going to kind of depend on the relative strengths of its conjugate acid and its conjugate base form. So the stronger the acid, the weaker its conjugate base. And the stronger the base, the weaker the conjugate acid. What this means is that if you have a way to like stabilize the conjugate base, if you have something like resonance or induction or something like this to stabilize the conjugate base, then you're going to make it so that that base is less likely to act as a base. And so you're going to be more likely to find it in that base form. So it can get kind of confusing because the stronger the acid is, the more likely you are to find it in the conjugate base form. And the stronger the base is, the more likely you are to find it in the conjugate acid form. So when you're trying to predict whether an acid will be stronger or weaker, you need to be thinking about, well, which of these forms is going to be more stable? And the more stable form is the happier form, the more thermodynamically favorable form, that's the form that you're going to find it in. So it's important to remember that something can only act as an acid in its protonated state. But the stronger the acid is, the less likely it is to be in that state. And thus, the more likely it is to be in the deprotonated state. And in the deprotonated state, so that conjugate base form, well, now it can only act as a base. Once your friend gives up that cookie, it can only take a cookie. It doesn't have another cookie to give up. So if the molecule is neutral in its protonated state, though, if that's neutral in its conjugate acid, well, now when it deprotonates, it gives up that proton, that positively charged proton. Well, now it's going to be negatively charged in its conjugate base form. But some molecules are positively charged in their protonated state. So the conjugate acid is going to be positively charged, and therefore they'll be neutral in their deprotonated state, so in their conjugate base state. So we can't simply look at charge to tell us whether something is an acid or a base, or some acids are neutral in their protonated state and some are positively charged in their protonated state, but they're always going to be one charge less in their deprotonated state, but that could be neutral and that could be negatively charged. And this is all assuming that we're talking about a single site. So when we're talking about a single site, we can talk about in terms of the pKa for that site. When the pH equals the pKa, you have equal amounts of acid and base. If you're below that pKa, well, now that jar is fuller, there's more protons around, you're more likely to be protonated. But if you're above the pKa, well, now there's fewer protons around, that jar is more empty, and so you're more likely to be deprotonated. And this is true no matter what acid we're talking about. What's going to change is the pKa. Different acids, different deprotonizable sites are going to have different pKas. So the pKa is going to kind of set the cutoff point. Where is that 50-50 mark? Where is it that half of them will be protonated and half of it will be deprotonated? And so remember that if you have a stronger acid, basically what that means is you're going to have a lower pKa. That jar is going to be more full when you draw that 50-50 line because you're more generous. And if you have a higher pKa, we're going to be shifted to the right, and we're going to basically say that that jar has to be more empty before we can donate. So different acids will have different pKas, and therefore they'll be at different places within that spectrum.
There's this equation called the Henderson-Hasselbalch equation that allows you to go between a pH and pKa values in order to figure out things like what proportion of an acid is in the protonated or deprotonated state, as well as to calculate how much of the conjugate acid and conjugate base to mix together to get a buffer of a specific pH. And so those are the two main functions we're going to talk about using it for, but there are other things that you could do with it as well. And we'll get into some examples and things like that.
You can use the Henderson-Hasselbalch equation to figure out the actual proportions of things that are protonated or deprotonated at a different pH based on their pKa. It's also really important, though, to realize we don't even need to use the Henderson-Hasselbalch equation. So basically, for each pH unit away from the pKa that you go, you're going to get tenfold more of one form. And so if you go one pH unit above your pKa, well, now we're saying there are fewer free protons around. That cookie jar is more empty. So you're less likely to find things being protonated. You're more likely to have things in the deprotonated state in the 1 pH unit above. If you go 2 pH units above, well, now you're going to have 100-fold more of it in the deprotonated state. 3 pH units above, 1,000, 4, 10,000. So you can see that by the time you're a couple pH units away from the pKa, it's predominantly going to be in one form. And if we go the other direction, if we go below the pKa, well, now there's more protons available. So now we have like the opposite situation. We're going to get tenfold more of the protonated form, and then 100-fold more, and then 1,000-fold more, and then 10,000-fold more. So if we're a couple units away from the pKa, we don't even need to use the Henderson-Hasselbalch equation to know that almost all of it is going to be in one state. Another valuable thing about the pKa is because it's that 50-50 point at which there's equal amounts of your acid in your conjugate base, this makes a really great buffer.
A buffer is a solution where you have fairly equal concentrations of a conjugate acid and its conjugate base. So you're near the pKa of that acid. And that means that there's lots of the acid form and lots of the base form. So if you add a little acid, the base can pick up the protons. And if you add a little base, then the acid can donate some protons, and that'll keep the pH fairly stable when you're in that range around the pKa. So when you're in the lab and making a buffer, you're often going to look to a chart to see what the pKa of various buffer options are and choose a conjugate acid that has a pKa around where you want the pH to be, because at the pKa is where you have 50% protonated, 50% deprotonated, and therefore you're better able to counteract any added acid or base. So different conjugate acids, different buffer compounds will be better for different purposes. And you can look at charts to see what might be good for your applications.
So that was a simple case where we just have a single pKa to talk about. But as I mentioned, we often have complicated things in biochemistry. We have things where instead of a single pKa on a molecule, we have multiple. And we might have lots and lots and lots. So a multiprotic acid is like, instead of just inviting a bunch of separate friends, they all come together and they're linked together. Some of them are going to come with cookies and some of them are going to come hungry. And therefore, the pH of your solution is going to depend on all of these groups like before, but they're going to be on the same molecule. Depending on the pH, you'll find those friends with a cookie or without a cookie. And so now we can talk about a pKa value for each of those different groups, as well as a pi value. So a pi is the isoelectric point. It's the pH at which the molecule is neutral overall.
So you can think about it kind of like being that at the pi, there's an equal amount of friends with cookies and without cookies.
So some groups might be positive, some groups might be negative, and you are going to have this situation where your molecule overall is going to be neutral. The pH at which that happens is your pi. At a pH below the molecule's pi, so remember, pi is telling you about the molecule level. If you're at a pH below that, you're going to be positive most of the time. There's more protons around, more of the sites become protonated, you're going to be net positive. But that's coming from like all of these sites and everything. It's not telling you about like what specific site tipped the scale or anything like this. A pKa, remember, this is talking about a single ionizable site. It's saying that site is going to take a proton if you're at a lower pH, and so you're more likely to find it protonated. This does not tell you anything about charge. This only tells you about protonation at that individual site. Conversely, at a higher pH, there's going to be fewer protons available. If there are fewer protons available, then the molecules become more likely to give up those protons. They become less likely to have a proton. If they give one up, they can't find one. All these various things. If you're at a higher pH, you're less likely to find those protons. Those protons, remember, that's where the positivity is coming from. But that is happening at these pKa levels, not the pi level. And when we talk about the charge, that's the molecule overall, that's the pi. If you're at a pH that's above the pi, you're going to be negative most of the time. On net, that's the net, the whole molecule. If you're at a pH that's above an acid's pKa, that site is going to be deprotonated the majority of the time. So again, we're talking about site with a pKa versus talking about charge with the pi. Looking at the site, it does not tell us about the actual charge. The molecule is going to, yes, be in a decreased charge than it was before, but that we don't know anything about the charge of the molecule in its previous state. The pi refers distinctly to the charge, not to any one site. And when you're at the pi, when you're at a pH that's at the pi, now your molecule is going to be net neutral most of the time. And if you are at an acid's pKa, the acidic site is going to be protonated half the time and deprotonated half the time. This does not tell you anything about the charge of the overall molecule.
An example of such a multiprotic molecule are amino acids. So every amino acid has at least two pKa groups. It's got the pKa for the carboxylic acid group, and it's got the pKa for the amino group. And remember that the pKa is always going to be telling you about the acid form, about the protonated form. So if we talk about the carboxylic acid form, so if we talk about this COOH, sometimes we refer to this as the pK1, and that's going to be the pKa for this COOH group, and typically that's about 2. It's going to vary a little between the different amino acids for different reasons, including inductive effects and things like this that are making the thing more or less acidic. But when we're talking about our pK1, this is going to be the pK1. And you'll see that all amino acids are going to have this pK1. Well, at least in their free floating form, these are going to have that carboxylic acid group. Now, all the amino acids are also going to have a pK2. And the pK2, this is going to correspond to this. So that's going to be our pK2, and that's going to be typically about 9 to 10. That's going to be the pKa for the NH3 plus group, because remember that the pKa is always going to tell us about the acid form. So the pK2 is going to tell us about the strength of this protonated amine group on our amino acid. And note that it has a higher pKa though, so it's a weaker acid than our carboxylic acid. And well, what did we say before? We said if something was a stronger acid, we're more likely to find it in its conjugate base form because it wants to act as an acid. And so once it acts as an acid, it's in its conjugate base form. So for our carboxylic acid group, we're going to typically find it in its deprotonated state, in its conjugate base state. But for our amino group, well, here we're saying, okay, well, we have a weaker acid, which means we're more likely to find it as an acid, which means that we're more likely to find it in this protonated state. But of course, this is going to depend on the pH, right? We can compare the two of them and say, yeah, we're more likely to find the COOH deprotonated than we are the NH3 group. But that's all going to depend on the pH. So if you're at a low enough pH, that's going to happen is that both of those groups are going to be protonated. Both of them are going to be in their conjugate acid form. But then as you go up, basically first you're going to go past that first pKa, that pKa for your carboxylic acid group. That's going to deprotonate first, because remember that things are going to deprotonate in the order of increasing pKa. So that carboxylic acid group is going to deprotonate. And then what's going to happen is that the amino group, this is still going to be protonated. But then what's going to happen if you increase the pH even more, well, now you get that deprotonation of your amino group. And so now you get the conjugate base form. But you have to get to a pH of about 9 to 10 in order for half of that to be deprotonated. So instead, what you're going to find typically is you're going to find that at a pH in our body, you're going to have it in this Witter ionic form where you have a positive charge on the amine group and a negative charge on your carboxyl group. But there's a specific point at which it's exactly like ionically neutral. Because remember, there's going to be some of it in one form or some of it in another form, depending on how far you are away from the pH. And there's some pH when it's exactly even, when it's exactly neutral. And this is going to be your isoelectric point or your pi. If you only have 2 pKa groups, then the pi is simply the average of the 2. Things get more complicated if you have multiple groups, but if you just have 2, it's just going to be the average of them. So if we take the average of about 2 and about 10, so 2 plus 10 is 12 divided by 2, that gives us about 6 for our isoelectric point, the point at which something is electrically neutral. So isoelectric point, something is electrically neutral. And this is something that's like a multiprotic thing. It can be an amino acid, it can be a different multiprotic acid, or we'll see later, we can talk about it in the case of even more complex molecules like proteins, where we have lots and lots of different sites. And with all of those cases, we can use this term pi to refer to the isoelectric point, the point at which it's net neutral. If you just have 2 sites and one of them is positive when it's protonated and one of it is neutral when it's protonated, then your pi would just be the average of the 2 pKa's. But if you have more, then you have to kind of think through things a little to think about where you would have that 0 point, because that 0 point is going to come when in between the pKa's for 2 of them. If you were to look at a chart of amino acids and their different pKa values, what you'll see is that things are actually more complicated. So instead of all of them being nice like glycine and just having 2 pKa values, sometimes what we get is we get an ionizable side group. And so what we get is we get a pKr. So the pKr equals the pKa for an R group of an amino acid. That's going to be our pKr. And you'll see that only some of them are going to have pKr values. And this is because only some of them have ionizable side chains. Note too that in the context of a protein, the pKr can be totally skewed, as well as those pKa values for the ends. So context really, really matters, and we'll see how things around the amino acid can greatly influence the pKr or the pKa. But looking at these tables can be helpful for you to kind of get a sense. The main ones that we talk about when we talk about like ionizable ones are going to be histidine, lysine, arginine, aspartic acid or aspartate, and glutamic acid / glutamate. These are going to be the main ones we talk about, but then tyrosine and cysteine can also ionize, and so you'll find pKr values for them as well. And I'm going to want you to do the same sorts of things for those. But the naming can get kind of confusing because, well, anytime we have a weak acid, we're going to have to talk about its conjugate base as well. And we talk about things going back and forth between the acid and the base. So how do we choose whether we call something basic or we call something acidic? In the case of amino acids, it's based on their neutral form. So let's think first about what's the predominant form at a pH of 7.4. How are we going to go about this? Well, we can go about this by comparing their pKa to the pH. Remember that at a higher pH, there's going to be less protons available. And at a lower pH, there's going to be more protons available. And so what's going to happen is that if you are at a pH that is above your pKa, this means that you're more likely to be in the deprotonated state. But if you're at a pH that is below your pKa, well, now you're more likely to be in the protonated state. And so the pKa, remember, that's going to tell us where we draw that 50-50 line. If that pKa is lower, then we're more likely to be above it. And if that pKa is higher, we're more likely to be below it. And so more specifically, in the case of aspartic acid, say, well, here it's got a pKa of about 4, and we're talking a pH of about 7.4. So we're talking like 3 pH units away or so. We've got about 1,000-fold more in its deprotonated state. And so for aspartate, we're more likely to find it in its deprotonated state. Glutamate, same deal. What about the basic ones? So histidine is a little bit confusing because histidine is kind of wishy-washy. It's got a pKa that's closer to our pH we're talking about. So you still have significant amounts of histidine in both forms, but which form are you going to have more of it in? Remember that we're still above the pKa. This means that we're going to have more of it in its deprotonated form. What about lysine and arginine, though? These guys have higher pKas. Now we're talking pKas that are above the pH that we're at. And since the pKas are above that, basically what that means is you've got to get that cookie jar really, really full before they donate. And so in this state, the cookie jar is full enough for them. And so they're saying like, no, I'm not donating. There's plenty in there. And so for these guys, you're going to find it in its protonated state. So these are going to be the predominant forms that we're going to see. Although with histidine, you'll also see some of each. But the predominant form, the main form, would actually be that deprotonated form. Okay, so now in that main form, is it acting as an acid or as a base? So remember back to what we talked about how you need to be protonated in order to be an acid. You need to have a cookie in order to give a cookie. If you're not protonated, you can't act as an acid. So let's look at each of these in turn. If we talk about aspartate and we talk about glutamate, we said that they were more likely to be in their deprotonated state, as well as histidine. In that form, is it going to act as an acid or is it going to act as a base? Well, it can only act as a base, so those are going to act as bases. And well, what about lysine and arginine? We said that they're more likely to be in their protonated form. They're more likely to have cookies. So they can't take another cookie, their hands are full. Instead, they can only donate a cookie. They can only act as an acid. So in those dominant forms, those ones we call basic, a lot of them are actually acting as acids. Lysine and arginine, those are going to be acting as acids. And those ones that we call acidic, aspartate and glutamate, well, they're going to be acting in the conjugate base form. They're going to be acting as bases. But the thing is that they don't want to act as a base very much. And those basic amino acids, their conjugate acids, don't really want to act as acids. And so what they're done, then they're not gonna. And so they were so happy acting as an acid, or they were so happy acting as a base, that we're gonna find them in their conjugate form. We're gonna find them as they've already done that. Those cookie monsters have already taken a cookie in the case of the basic amino acids, or they've given up a cookie in the case of the acidic ones. And so then why do we call these basic, or why do we call them acidic? Well, that's because we need to think about their neutral form. The naming is based on whether their neutral form acted as an acid or as a base. So even in the case of histidine, even though unlike those other guys, it actually has a pKa that's below the pH we're normally talking about, well, even then, in its neutral form, it's going to act as a base and pick up that proton. And for the basic amino acids in their neutral form, well, that's the deprotonated state. And so they're also going to act as a base in the deprotonated state, which is their neutral state. But in the case of our acidic amino acids, well, they're in their neutral state, they're going to be protonated. So unlike those otherwise, when these are protonated, they're neutral. And thus, when they're protonated, that's when they're going to act as an acid. And so we call these the acidic amino acids. The same things are going to apply when we talk about general acid, general base catalysis. Here, we will see our acidic amino acids acting as bases and our basic amino acids acting as acids, but we'll also see them doing the opposite, because if something is able to donate a proton, it's able to take a proton. Especially in the context of an enzyme active site, enzymes speed up reactions and don't get used up in the process. So they have to be able to reset and do things over and over again. So we'll see these acidic and basic amino acids, as well as some of the other ones, work as both general acids and general bases. So some key takeaways. Something can only act as an acid in its protonated state. And so remember that we use HA to represent like a generic weak acid. So that's your friend that comes with a cookie. Only the friends that come with cookies are able to actually donate cookies. And so you're only going to talk about acting as an acid when something's in its protonated state. However, this could be positively charged or it could be neutral. But regardless, you have that friend that comes with a cookie. Well, now some of your friends are going to be really generous and they're going to donate a cookie, even when the jar is pretty full. And those are going to be your stronger acids. There are going to be other friends that they're not as likely to donate a cookie. And so they kind of want that cookie for themselves. They're going to be a weaker acid. It's not until that jar gets pretty empty that they're going to donate. And so that would be like your weaker acid. That would be something that would have a higher pKa, meaning that that jar has to be more empty in order for them to actually donate. And remember, it's not that simple. It's more just that they have a higher affinity for that proton, and so they're more likely to keep latched onto it and less likely, therefore, to give it up. And then if there's a lower availability around it, well, now if it accidentally drops that cookie, it can't find another cookie. But basically, when we talk about the pKa, we're talking about the strength of the acid. But the stronger the acid is, the more likely it is to actually act as an acid. And if it acts as an acid, well, it gives up that cookie, and now you're less likely to find it with the cookie. And so if you have a stronger acid, you're more likely to find it in its conjugate base form. And if you have a weaker acid, well, now you're more likely to find it in its acid form. And so it can get kind of confusing when we talk about the naming of things like amino acids. We're going to be classifying them as basic or acidic based on their neutral state. So how is something a stronger acid or a stronger base? Well, it has to do with comparing the strength of the conjugate acid and the conjugate base. It has to do with comparing the stability of them. Form that you're more stable in, that you're more happy in, that's going to be the state that you're going to be finding it in. And so if you can use something like resonance or induction to stabilize one of the states, to stabilize charge, that's going to make that state more favorable. And so you can have resonance be contributing to both a higher pKa as well as to a lower pKa. Now, proteins are going to have a lot of these different side chains that are going to be ionizable. And so what's going to happen is you're going to have a combination of amino acids in the protein that are going to be positive and negatively charged. At some point, at some pH, you're going to have it where they balance out. The pH at which this happens is the pi. Pi is the point at which you've got that even balance. Your protein is on net neutral. So again, this is not saying that none of the groups are ionized. In fact, if none of the groups were ionized, your protein probably wouldn't be very soluble. But instead, because those groups have different pKa values or different pKr values, we can call them, remember, they're going to deprotonate or protonate at different kind of like extremes and to different extents. And so what's going to happen, there's going to be some pH where you're going to be neutral. That is your isoelectric point. So now going back to our cookie jar analogy, got a whole busload of friends that are all connected. And some of these are going to burn cookies and some of them are going to want cookies. And so now we have to calculate the pi for that. Thank goodness for computers, right? And so we can use a computer program like xpesi-prop-param in order to calculate theoretical pi for a protein, in order to do things like figure out the overall charge of a protein when you're trying to figure out a purification strategy that is charge-based. Because remember, the pi is the point at which you're neutral. Below that, more protons, more of it gets protonated. The protonated outweigh the deprotonated, your protein becomes positive. At a higher pH, there's fewer protons available. Less of those sites are going to be protonated. You're going to have your protein be negative. You can do things in the lab, like take advantage of this relationship between the pH and the pi in order to separate proteins based on their charge. Because different proteins have different PIs, they have different charges of the same pH. We can use this to separate proteins based on their charge. Use these little resonance, little beads that are charged. If your protein is positively charged at the pH of your buffer, you're going to want to use negatively charged beads. And if you are going to be purifying a protein that is negatively charged, you're going to want to use positively charged beads. The pi is referring to the isoelectric point, the point at which you have this net neutral. This is not telling you about the individual sites. If you want the individual sites, you go to the pKa, and the pKa in the terms of a protein is going to be your pKr. If we're not counting the pKa's of the carboxyl ends and the amino terminus, it's also really important to know that when they link together, their pKa's can change dramatically. Just like a stronger acid is going to have a lower pKa, a more acidic protein is going to have a lower pi. So we talk about an acidic protein versus a basic protein. Typically, the acidic proteins are going to have a lower pi, and the basic proteins are going to have a higher pi. And that comes from the combinations of acidic and basic side chains and how many there are of each and which ones there are, and all of this context stuff. But you're going to say that a lower pi is going to be a more acidic protein, and a higher pi is going to be a more basic protein. Speaking of acidic proteins, typically we're going to find them after a lot of those sites have acted as acids, and so you're going to find it negatively charged. If we talk about an acidic patch on a protein, that's going to be a part of the protein where there's a lot of those acidic residues. So remember, residue is just the remainder when those amino acids join together and their side chains stick out, but they've lost their amino and their carboxyl groups because those have combined to form the peptide bond. In the residue, you're going to have these acidic residues. Those are going to make it an acidic site. And then you're going to have that colored red often. And then if you were to have a basic site, a basic patch, that would have a lot of those basic residues, those lysines, histidines, arginines, and those would give it a positive charge in that region and be colored blue. And in those positive charge forms, those are the conjugate acid forms of those basic amino acids. Key thing, pi, charge, pKa, individual acidic site. pKr is just the name for the pKa of an amino acid's R group, aka side chain. And pH is telling you at the solution level. And you compare the pH to the pKa or to the pi or to the pKr in order to figure out what state things are. The more protons there are, the lower the pH. The lower the pH, the more likely things are to be protonated. Remember, protons come with positivity. So if your pH below the pi, that's telling you your molecule is going to be positive. If you, however, are at a pH below the pKa, well, all this is telling you is that that acidic site is going to be protonated. That does not mean that the site is going to be positively charged, or the molecule as part of it is going to be positively charged. We see these terms often in the case of a protein At the pKa, you're going to have equal amounts protonated and deprotonated of the side chain ionizable group, just like you would have for any other acid, but we give it this special name, this pKa.